What if size itself breaks down? Tonight, we're going to explore the largest thing in the universe. Something so vast it challenges our ability to even call it an object. You've probably heard terms like galaxy or universe thousands of times. But here's what most people don't realize. The biggest structures we've discovered are so enormous that our galaxy, containing 200 billion stars, becomes completely invisible within them. By the end of this journey, you're going to understand why the search for the largest object reveals more about the limits of human comprehension than about space itself. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes it. Let's begin. Picture yourself standing at the center of a football field. The grass stretches out in every direction. And if you had to run from one goal to the other, it would take you a good minute or two of intense sprinting. That field feels massive when you're crossing it on foot, doesn't it? Your legs burning, your lungs working hard. The distant goal posts seeming impossibly far away during those 90 minutes of play. Now imagine rising above that field in a helicopter, slowly ascending until the entire stadium comes into view. What seemed enormous moments ago, that vast expanse of green, suddenly becomes just a small oval patch. You can see the parking lots, the surrounding streets, thousands of buildings stretching to the horizon. The field that felt infinite when you were running across it is now just a tiny geometric shape in a sea of human construction. This is where our journey begins. With this simple shift in perspective that reveals something profound about how our minds work. Your brain evolved over millions of years to understand distances you could walk, objects you could touch, spaces you could cross in a day's journey. When our ancestors looked across a valley or up at a mountain, they were seeing the absolute limits of what seemed comprehensible. A day's walk, a week's travel, the horizon where the earth met the sky. But we're about to venture into realms where your intuition will not just fail, it will become completely meaningless. Think of a small ant at the very center of that football field we imagined. From the ant's perspective, the grass extends infinitely in all directions. Those goalposts, they might as well not exist. The ant cannot even conceive that there are boundaries to its world, let alone imagine the stadium, the city, the continent beyond. We are about to discover that we are that ant, and the structures we're going to explore would make our entire galaxy invisible from their edges. Let me share something that might sound impossible at first. The largest known structure in the universe is so unimaginably vast that light, traveling at 300,000 kilometers per second, would need more than 1 billion years to cross from one side to the other. Light, which can circle the Earth 7.5 times in a single second, would spend 1 billion years just trying to traverse this single cosmic structure. To help you grasp this scale, imagine if the entire Earth, our home, with all its oceans and continents and billions of people, were compressed down to the size of a pinhead. Even at that impossible compression, this cosmic object would still be larger than the entire American continent stretched from the North Pole to the South Pole. Do you feel it? That moment when numbers become so large, they stop meaning anything. When words like gigantic or colossal suddenly feel as inadequate as calling the ocean damp, we've reached the point where human language itself begins to break down. There are no words in any language that were designed to describe structures that dwarf entire galaxies. Here's something that puts our recent discoveries in perspective. Just 100 years ago, in the 1920s, humanity believed that our galaxy, the Milky Way, was the entire universe. Everything that existed. The whole of reality. We had no idea that beyond our stellar neighborhood lay billions upon billions of other galaxies, each containing hundreds of billions of stars. It was only in the last few decades that we've begun to map the true architecture of the cosmos, and what we've found challenges everything we thought we knew about size itself. The journey we're about to take together will start here, with objects you can relate to. We'll move through planets and stars, then venture into the vast spaces between stellar systems. We'll explore entire galaxies, then groups of galaxies, then structures so large they make galaxy clusters look like specks of dust. Until finally, we reach the very limits of what can physically exist. Prepare yourself for a revelation that will reshape how you think about everything. Our human intuition about size, about what's big and what's small, about what matters and what doesn't, it's all about to be turned completely upside down. The reality of the cosmos is stranger and more magnificent than any science fiction ever dreamed. But before we venture into those impossible realms, we need to establish our cosmic measuring stick. In everyday life, you think in meters and kilometers. When you drive to the next city, it might be 100 kilometers away. When you fly across an ocean, it's thousands of kilometers. But in space, these measurements become laughably inadequate. A light year, the distance light travels in 1 year, equals approximately 10 trillion kilometers. 10 trillion. That's a number so large that if you tried to count to it, spending 1 second on each number, it would take you over 300,000 years. The sun, which floods our world with light and warmth, measures about 1.4 million kilometers across. From Earth, it looks like a modest disk in the sky, something you could cover with your thumb at arm's length. But if the sun were hollow, you could fit over 1 million Earths inside it. And yet, in the scale we're building toward, our sun will soon seem like an invisible speck. Here's a comparison that might help you visualize our solar system. If you scaled the sun down to the size of a basketball, our Earth would be a grain of black pepper about 26 meters away from that orange sphere. 26 meters. You could walk that distance in about 20 seconds, but in real space, that represents 150 million kilometers. The distance light takes 8 minutes to travel. Now let's take the next step outward. Our Milky Way galaxy contains more than 200 billion stars like our sun, each one a nuclear furnace, many with their own family of planets. These stars are arranged in a beautiful spiral structure that spans 100,000 light-years from edge to edge. Try to picture this. If each star in our galaxy were a single grain of sand, you would need a beach 16 kilometers long to lay them all out in a single line. 16 kilometers of sand grains, each one representing an entire solar system. And our galaxy is just one among trillions. But here's where our journey takes its first breathtaking leap: the Milky Way, with all its majesty and all those billions of stars, is merely a tiny component in structures called cosmic filaments. These filaments stretch across billions of light years, connecting vast regions of space like an intricate web spanning the entire observable universe. Imagine our galaxy as a single house in a city. These cosmic filaments would be like entire continents covered with millions upon millions of such cities, all connected by invisible highways of dark matter and energy. The scale is so vast that our home galaxy, containing everything we've ever known or could ever hope to explore, becomes just one microscopic point of light in these cosmic superhighways. To truly understand what we're about to discover, you need to prepare yourself psychologically for something that your mind was never designed to comprehend. We must abandon our human intuition about distance, about size, about what it means for something to be large. The familiar concepts that guide your daily life, the distance to your work, the size of your city, even the size of your country, will become utterly meaningless. Think about this for a moment. How is it possible that we, human beings who live for less than a century on a planet that's just a tiny rock orbiting an ordinary star, have managed to discover and map structures that are larger than trillions of solar systems? How did we develop the tools and the understanding to measure things that are literally billions of times larger than anything in our direct experience? The answer lies in one of humanity's greatest achievements: our ability to extend our senses through technology and our capacity to think beyond the immediate and tangible. Every photon of light that reaches our telescopes is a messenger from the deep cosmos, carrying information about structures so vast they existed billions of years before Earth even formed. We've learned to read the language of light itself, to decode the stories it tells about distance and time and the architecture of space. When you look up at the night sky, you're not just seeing pretty lights, you're seeing the visible tips of cosmic icebergs, the nearby endpoints of structures that stretch across distances your imagination cannot truly grasp. As we continue this journey together, moving step by step from the familiar to the impossible, remember this: every step we take outward reveals not just the magnificent scale of the universe, but the equally magnificent capacity of human consciousness to reach beyond its evolutionary limits and touch the infinite. Now that we've established our human perspective and prepared our minds for what's coming, we're ready to begin our cosmic ascent. We'll start with our own solar system, our local cosmic neighborhood, and then venture outward into the vast spaces between the stars, towards structures so large that they redefine what it means for something to exist at all. Our solar system serves as the perfect launching pad for understanding cosmic scale. From the orbit of Pluto at its farthest reach, our entire solar family spans approximately 12 billion kilometers in diameter. To put this in perspective, this is a distance that would take our fastest spacecraft decades to traverse, even traveling at speeds that would circle Earth in just a few hours. But let's shrink this down to something more manageable for our minds. Imagine compressing our entire solar system, the Sun, all the planets, all their moons, the asteroid belt, everything we call home, down to the size of a single grain of sand. You could hold it between your thumb and forefinger. Now, where would you find the nearest star, Proxima Centauri? You'd have to walk 4 full meters away from that grain of sand. 4 meters. That's the distance across a small room. Think about that for a moment. If our entire solar system, with all its planets and the vast spaces between them, becomes a grain of sand, the nearest star is still 4 meters away. This reveals something profound about the nature of space itself. The universe is not crowded. It is not bustling with activity everywhere you look. It is mostly empty. Voyager 1, humanity's most distant ambassador, has been traveling through space since 1977. It's currently moving at 17 kilometers per second, fast enough to cross the United States in about 5 minutes. Yet at this incredible speed, it would take Voyager more than 73,000 years to reach Proxima Centauri. 73,000 years. That's longer than the entire span of recorded human history. Let's examine our stellar neighborhood more carefully. Within 12 light years of our Sun, there are only 26 star systems. 26. In a sphere of space so vast that light takes 12 years to cross it, we find fewer stellar neighbors than the number of letters in the alphabet. To help you visualize this cosmic loneliness, imagine a stadium filled with 100,000 people. Now imagine that each person represents a star, but instead of being seated next to each other, each person is separated by 400 kilometers. 400 kilometers. You could drive for 4 hours on a highway and still not reach your nearest neighbor. This is the reality of stellar distances, an isolation so profound it challenges our understanding of what it means for things to be close to each other. When you look up at the night sky on a clear evening, you might see about 6,000 stars with your naked eye, 6,000 points of light scattered across the celestial dome. It feels like a lot, doesn't it? Like the sky is filled with stars. But those 6,000 stars represent less than 1/100th of 1% of the stars in our galaxy alone. Less than 0.01%. What you're seeing is the tiniest sample of our galactic neighborhood. Here's something that puts our recent cosmic awakening in perspective. Until 1925, less than a century ago, astronomers believed that our Milky Way galaxy was the entire universe, everything that existed. When they looked through their telescopes and saw fuzzy patches of light called nebulae, they assumed these were clouds of gas and dust within our own galaxy. Then came a discovery that changed everything. Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory, made observations that shattered our cosmic perspective forever. He was studying the Andromeda Nebula, measuring the brightness of certain variable stars within it. When he calculated the distance to these stars, he found something impossible. They were far too distant to be part of our galaxy. The Andromeda Nebula wasn't a nebula at all. It was an entire galaxy, a separate island universe containing hundreds of billions of stars, located 2.5 million light-years away from us. In a single observation, Hubble had doubled the size of the known universe and revealed that we lived in a cosmos filled with other galaxies. Andromeda stretches across 1 trillion stars, twice as many as our own Milky Way. Imagine trying to count the stars in Andromeda. If you counted one star every second, without sleeping, without stopping, it would take you over 31,000 years to count them all. And that's just one galaxy among trillions. Think of it this way: if our local stellar neighborhood were a small swimming pool, our entire Milky Way galaxy would be like the Atlantic Ocean, vast, deep, containing currents and regions we've barely begun to explore. And Andromeda would be the Pacific Ocean, sitting thousands of kilometers away, an entirely separate body of water with its own weather patterns, its own ecosystems, its own untold mysteries. But the story doesn't end with 2 galaxies floating in empty space. Our Milky Way, Andromeda, and more than 80 smaller galaxies are all gravitationally bound together in what astronomers call the local group. This cosmic family extends across 10 million light-years, held together by invisible threads of gravity that have been weaving this stellar tapestry for billions of years. Yet even the local group, with all its galaxies and trillions of stars, is merely a small suburb in something much larger. We exist within the Virgo supercluster, a vast collection of more than 300 galaxy clusters, each cluster containing hundreds or thousands of galaxies like ours. To visualize this hierarchy of cosmic structures, imagine the local group as a tennis ball. The Virgo supercluster would be an entire basketball court filled with thousands of such tennis balls, each ball representing a group of galaxies, each galaxy containing billions of stars, each star potentially hosting worlds we can barely imagine. And our entire cosmic neighborhood is in motion. The Milky Way galaxy is racing through space at 600 kilometers per second, that's over 2 million kilometers per hour, pulled by the gravity of something called the Great Attractor. This mysterious gravitational anomaly has the mass of tens of thousands of galaxies. Yet we can't see it directly because it lies behind the dust and stars of our own galactic plane. The great attractor remains hidden in what astronomers call the zone of avoidance, a region of sky obscured by our own galaxy's disk. But we know it's there because we can measure its gravitational influence on thousands of galaxies across hundreds of millions of light years. Entire galaxy clusters are streaming toward this invisible gravitational giant, like leaves caught in a cosmic river. The spaces between galaxies contain almost nothing by earthly standards, approximately 1 hydrogen atom per cubic meter. To put this in perspective, the best vacuum chambers on Earth contain billions of times more particles than the space between galaxies. If you could take a cubic meter of the emptiest space we can create in our laboratories and remove 99% of the remaining particles, you'd begin to approach the density of intergalactic space. Yet even this apparent emptiness is filled with something remarkable. The entire universe is bathed in a faint glow of radiation left over from the Big Bang itself. This cosmic microwave background radiation fills every cubic centimeter of space with photons that began their journey 13.8 billion years ago, when the universe first became transparent to light. The temperature of this primordial glow is just 2.7 degrees above absolute zero, the cold echo of creation itself. Our ability to detect and study these vast structures depends on instruments that extend our senses across impossible distances. The Hubble Space Telescope has been our eye in the sky for over 3 decades, peering into the deep cosmos and revealing galaxies so distant that we see them as they were billions of years ago, when the universe was young. Now, the James Webb Space Telescope pushes even deeper into space and time, showing us the first galaxies that formed after the cosmic dark ages. When we observe these distant galaxies, we're not just looking across space, we're looking back in time. The light from a galaxy 1 billion light years away left that galaxy 1 billion years ago. We're seeing it as it was before complex life appeared on Earth. In the most distant galaxies we can observe, we see light that began its journey when the universe was just a few 100 million years old. To truly understand the structures we're about to explore, the largest objects in the known universe, we need to completely reimagine what we mean by object. We must think of entire galaxies, each containing hundreds of billions of stars, as single points of light in a vast three-dimensional web that spans the entire observable universe. This cosmic web is not a human construction or metaphor. It's the actual architecture of reality. Galaxies are not scattered randomly through space, like stars thrown across a dark sky. They lie along vast filaments of dark matter and normal matter, connected in a network that looks remarkably like the neural pathways in a brain or the structure of a vast biological cell. The scale of this cosmic web is so enormous that our entire journey so far, from our solar system to our local group to the Virgo supercluster, has taken us through just the tiniest local region of a single cosmic neighborhood. We've been exploring the cosmic equivalent of a few city blocks, unaware that we live in a universe-sized metropolis. Now that we understand our local cosmic context, our solar system, our stellar neighborhood, our galaxy group, and our supercluster, we're ready to expand our perspective to structures where entire galaxies become the basic building blocks. We're about to explore cosmic architecture, where our Milky Way, with all its magnificent spiral arms and hundreds of billions of stars, becomes just one brick in construction so vast they redefine what it means for something to exist at all. When astronomers began to map the distribution of galaxies beyond our local cosmic neighborhood, they discovered something that fundamentally changed our understanding of the universe's architecture. Galaxies weren't scattered randomly through space like dust motes floating in sunlight. Instead, they were organized into vast clusters, gravitationally bound collections of hundreds or thousands of galaxies held together by invisible threads of dark matter. A typical galaxy cluster contains between 100 and 1,000 galaxies, all orbiting within a region that spans 2 to 15 million light-years. To put this in perspective, if our local group is like a small town, these clusters are like entire countries filled with galactic cities. Consider the Coma cluster, located 300 million light-years from us. This single cluster contains over 1,000 galaxies, each galaxy itself home to hundreds of billions of stars. The total mass of the Coma cluster equals 15 trillion times the mass of our Sun. 15 trillion. If you could somehow place our Sun on one side of a cosmic balance scale, you'd need 15 trillion identical suns on the other side to balance the Coma cluster. Let's expand our urban analogy to help grasp these scales. If each galaxy were a city with millions of inhabitants, then a galaxy cluster would be like an entire country, the United States or Brazil, filled with thousands of such cities. And the cosmic filaments we're about to explore? They would be like vast continents connecting different countries through invisible highways that span billions of light years. But here's where our journey takes a strange turn into the realm of the invisible. 85% of the matter in these galaxy clusters is something called dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We can't see it directly, but we know it's there because we can observe its gravitational effects on the galaxies we can see. The dark matter in galaxy clusters is so massive that it actually warps the fabric of space-time itself. When light from distant galaxies passes through a cluster, that light gets bent and twisted by the gravitational field of the dark matter, creating multiple distorted images of the same galaxy, like looking at yourself in a funhouse mirror that stretches across millions of light years. Between the galaxies in these clusters lies something equally extraordinary: a thin plasma heated to 50 million degrees Celsius. This intergalactic gas is so hot it glows in X-rays. Detectable only by specialized space telescopes like the Chandra X-ray Observatory. The temperature is so extreme that if you could somehow transport a small sample of this plasma to Earth, it would instantly vaporize anything within thousands of kilometers. In the 1980s, astronomers mapping thousands of galaxy positions made a discovery that revolutionized cosmology. Galaxy clusters weren't distributed randomly throughout space. Instead, they were connected by vast filamentary structures that stretched across billions of light years. This cosmic web, as it came to be known, revealed the true large-scale architecture of the universe. Picture the foam on top of your coffee, or the bubbles in a glass of champagne. The universe's structure resembles this foam, where galaxies lie along the thin walls between bubbles, and vast empty regions, the voids, occupy the bubble interiors. These cosmic filaments are like the scaffolding of creation itself, the framework upon which all visible matter hangs. The filaments function as cosmic highways, channels through which matter flows across the universe. Dark matter streams along these pathways, carrying ordinary matter with it, feeding the growth of galaxy clusters at the intersections where multiple filaments meet. It's as if the universe has a circulatory system, with filaments as arteries carrying the lifeblood of galaxies through cosmic space. The first of these colossal structures to be discovered was the CFA2 Great Wall, named after the Center for Astrophysics, where astronomers first mapped it. This wall of galaxies stretches 500 million light-years in length and 15 million light-years in thickness. If Earth were a marble, this structure would extend more than 100 kilometers in length, a cosmic membrane impossible to visualize in its entirety. But the CFA2 Great Wall was just the beginning. In 2003, astronomers discovered the Sloan Great Wall, a structure 3 times larger, spanning 1.4 billion light-years from end to end. To cross this structure, even at the speed of light, would take longer than the time that has elapsed since the first complex cells appeared on Earth. Within this cosmic web, the superclusters we explored earlier, like our home Virgo supercluster, are revealed to be merely dense nodes where multiple filaments intersect. Think of them as cosmic pearls strung along the threads of an incomprehensibly vast necklace, each pearl containing thousands of galaxies, each galaxy containing billions of stars. Between these filaments lie the cosmic voids, regions of space so empty they've earned names like the Butter's Void. Also known as the Great Nothing, this particular void spans 330 million light-years and contains almost no galaxies at all. If you lived in a galaxy within the Butter's Void, your night sky would be almost completely dark. No nearby galaxies, no stellar neighbors, just an ocean of emptiness stretching in every direction. The contrast in density is staggering. While cosmic filaments can contain 10 times the average density of matter in the universe, the voids contain only 10% of that average. It's as if matter has been squeezed out of these regions entirely, creating a cosmic Swiss cheese where the holes occupy 95% of the total volume. Within the filaments themselves, galaxies don't just sit stationary. They flow like rivers of light, streaming along the dark matter scaffolding toward the massive clusters at filament intersections. These galactic currents can be traced for millions of light years, revealing the dynamic nature of cosmic structure. The universe isn't static, it's a flowing, evolving network of matter and energy. The driving force behind this magnificent architecture is gravity, specifically the gravity of dark matter working over billions of years. In the early universe, tiny fluctuations in the density of dark matter began to grow under their own gravitational attraction. Over 8 billion years. These small variations evolved into the cosmic web we see today, with ordinary matter following the gravitational wells carved out by dark matter. This process began shortly after the Big Bang, when the universe was smooth and nearly featureless. Quantum fluctuations, random variations in density at the smallest scales, provided the seeds from which all cosmic structure would eventually grow. Over billions of years, gravity amplified these tiny differences, pulling matter into the filamentary network that now defines the large-scale structure of the cosmos. Think about the timescales involved. These structures took longer to form than Earth has existed. When the cosmic web was just beginning to take shape, our solar system was still billions of years in the future. The light from the most distant parts of these structures began its journey toward us when the universe was less than half its current age. As we observe these cosmic filaments stretching across billions of light years, we're seeing the largest confirmed structures in the known universe. They represent the limit of what we can definitively map and measure with our current technology and understanding. Each filament contains thousands of galaxy clusters, millions of individual galaxies, and trillions upon trillions of stars. Yet even these magnificent structures spanning distances so vast that light takes billions of years to cross them, are merely the neighborhoods of something even larger. We've been exploring the cosmic equivalent of city districts, unaware that they're part of an urban landscape so vast it challenges our understanding of what it means for something to be a single, coherent entity. The cosmic web filaments we've explored represent the confirmed large-scale structure of the universe, the scaffolding upon which everything else hangs. But astronomers have begun to detect hints of something even more extraordinary. Structures so large they approach the very limits of what can physically exist. Formations so vast they force us to reconsider our fundamental assumptions about the nature of cosmic architecture itself. We're now ready to venture beyond these confirmed structures into realms where individual galaxies become invisible points of light, where entire galaxy clusters appear as mere specks, and where we encounter the largest constructions that have ever been discovered in the observable universe. As astronomers pushed their observations deeper into space and further back in time, they began to uncover structures that challenged everything we thought we knew about the maximum possible size of cosmic architecture. These discoveries revealed that the cosmic web filaments we explored were merely components of even more magnificent constructions. Our home galaxy, the Milky Way, along with our local group and the Virgo supercluster, all exist within something called Laniakea, a supercluster spanning 500 million light-years and containing more than 100,000 galaxies arranged in a complex, branching structure that defies easy description. The name Laniakea comes from Hawaiian, meaning immeasurable heaven, a fitting description for a structure containing approximately 10 to the 17th power solar masses. That's the number 10 followed by 17 zeros. To write out this number in full, you'd need a string of digits longer than this entire sentence. If each digit were the size of a letter on this page, the number representing Laniakea's mass would stretch across several city blocks. Laniakea wasn't discovered by looking through telescopes at distant galaxies. It was revealed by mapping the movement of 30,000 galaxies in three-dimensional space. Astronomers measured how fast each galaxy was moving and in which direction, creating a velocity map that revealed the underlying gravitational currents of our cosmic neighborhood. What they found was remarkable. Galaxies within Laniakea don't move randomly. They flow like rivers toward specific gravitational basins, particularly toward the Shapley supercluster, a massive collection of galaxy clusters that acts like a cosmic drain, pulling matter from across hundreds of millions of light years. Think of Laniakea as a vast watershed. Just as rainwater flows downhill through creeks and streams toward rivers and eventually the ocean, galaxies flow along gravitational gradients toward the densest concentrations of mass. Our entire galactic neighborhood is caught in this cosmic current, streaming toward destinations we can map but may never reach. But even Laniakea, vast as it is, has been overshadowed by more recent discoveries that push the boundaries of what we believed possible. In 2024, astronomers announced the discovery of the Quipu superstructure, a cosmic formation spanning 1.3 billion light-years and containing 200 quadrillion solar masses. The Quipu gets its name from the ancient Incan system of knotted ropes used for record-keeping, because this cosmic structure resembles a main filament with multiple branches extending outward like knots on a cord. Its scale is so immense that if you could somehow shrink it down proportionally, a structure spanning from Earth to the Moon would represent just a few kilometers of the Quipu's true extent. To help grasp the Quipu's mass, imagine that every grain of sand on every beach on Earth represents our sun. You would need 200 quintillion planets exactly like Earth, each covered in beaches of solar mass sand grains, to equal the total mass contained within this single cosmic structure. The Quipu is not alone. Astronomers have now identified 5 massive superstructures of similar scale: Shapley, Serpens Corona Borealis, Hercules, and Sculptor Pegasus. Together, these 5 cosmic giants contain 45% of all galaxy clusters, 30% of all galaxies, and 25% of all the matter in the observable universe. Think about that for a moment. Just 5 structures contain a quarter of everything that exists in the cosmos. Despite occupying only 13% of the observable universe's volume, these superstructures have gathered an enormous fraction of all matter into their gravitational embrace. The universe, it turns out, is even lumpier than we imagined. Yet even these confirmed superstructures pale in comparison to the most controversial cosmic structure ever detected: the Hercules Corona Borealis Great Wall. This potential structure spans 10 to 15 billion light-years, approaching the size of the observable universe itself. The Hercules Corona Borealis Great Wall wasn't discovered through traditional galaxy surveys. Instead, astronomers detected it by mapping gamma-ray bursts, the most energetic explosions in the universe, created when massive stars collapse into black holes. These bursts appeared to be correlated across vast distances, suggesting they might all lie within a single, impossibly large structure. But structures this large create a fundamental problem for cosmology. According to the cosmological principle, one of the foundational assumptions of modern astronomy, the universe should appear homogeneous when viewed on sufficiently large scales. Structures larger than 1.2 billion light-years violate this principle, suggesting our understanding of cosmic evolution might be incomplete. Imagine the universe as a painted wall viewed from far away. According to our theories, when you step back far enough, any texture or pattern should disappear, leaving only smooth, uniform color. But these superstructures are like raised reliefs on that wall, bumps so large they remain visible even from cosmic distances. More recently, astronomers have discovered additional structures that challenge our models even further. The Big Ring spans 3 billion light-years in a nearly perfect circle, while the giant arc stretches 3 billion light-years in a graceful curve across the cosmic sky. These structures are so large they can be seen across significant portions of our observable universe. These discoveries are forcing cosmologists to reconsider fundamental models of how the universe evolved from the smooth and nearly uniform state we observe in the cosmic microwave background to the highly structured cosmos we see today. The mathematical models that successfully explain smaller-scale structures begin to break down when applied to these cosmic giants. What makes these superstructures even more remarkable is that they're not static monuments frozen in space. Entire superstructures move through the cosmos at hundreds of kilometers per second, influenced by the gravitational pull of other massive structures that we're only beginning to detect. The gravitational influence of these superstructures extends far beyond their visible boundaries. They act as cosmic lenses, bending and distorting light from even more distant galaxies. When we observe the most remote regions of the universe, we're seeing them through the gravitational influence of these massive structures, which can magnify, distort, or multiply the images of background galaxies. This gravitational lensing effect means that these superstructures don't just occupy space. They actively shape our view of everything beyond them. They're like cosmic telescopes, focusing and redirecting light from the early universe. In some cases, we can see galaxies that would otherwise be too faint to detect, their light concentrated and brightened by the gravitational field of intervening superstructures. These structures also affect our measurements of cosmic expansion itself. The Hubble constant, the rate at which the universe is expanding, can appear different depending on which direction we look, because massive superstructures create regional variations in the cosmic flow. What we thought was a uniform expansion turns out to be modified by the gravitational influence of these cosmic giants. With our current telescopes, we can map structures out to about 10 billion light-years from Earth. Beyond that distance, individual galaxies become too faint to study in detail, and we lose the ability to trace the cosmic web's finest structure. But we know that the observable universe extends to nearly 14 billion light-years in all directions, and there's no reason to think that cosmic structure simply stops at the limits of our current detection abilities. As we push our observations to these extreme distances, we're not just looking far away in space, we're looking far back in time. The most distant superstructures we can detect show us the universe as it was billions of years ago, when these cosmic giants were still forming, still gathering matter from the cosmic web. The structures we've explored represent the absolute largest confirmed objects in the known universe. Each one spans distances so vast that light, the fastest thing in the cosmos, takes billions of years to cross from one end to the other. They contain masses equivalent to hundreds of quadrillions of suns. They influence the motion of matter across significant fractions of the observable universe. Yet as we stand at this threshold, having explored the largest confirmed structures that science has definitively mapped and measured, we face a profound question. Have we reached the absolute limits of cosmic architecture? Or does something even larger await discovery? Something so vast it would make even these superstructures appear small by comparison. Structures that might challenge our very understanding of what it means for something to exist as a single, coherent entity in our cosmos. To understand whether anything larger than these superstructures could exist, we must confront the ultimate boundary of cosmic observation, the observable universe itself. This spherical region around us has a diameter of 93 billion light-years. But this doesn't represent the edge of reality. It's simply the limit of what we can possibly see. Here lies one of the most mind-bending paradoxes in cosmology. Although our universe is only 13.8 billion years old, we can observe objects that are now 46.5 billion light-years away. How is this possible? The answer reveals something profound about the nature of space itself. Imagine running on a treadmill that's moving backward while you run forward. You might run steadily for an hour, but when the treadmill finally stops, you could find yourself much farther from your starting point than the distance you actually ran. This is what happened to light traveling through our expanding universe. When light from a distant galaxy began its journey toward us billions of years ago, that galaxy was much closer than it is now, but as the light traveled through space, the universe continued expanding, stretching the space between us and that galaxy. By the time the light reaches us, the galaxy has been carried much farther away by cosmic expansion. This creates a fundamental physical limit. No individual structure can be larger than the observable universe, because nothing could have formed beyond the distance that light has been able to travel since the Big Bang. The observable universe represents the absolute boundary of causal connection, the maximum distance across which any influence or information could have traveled since the beginning of time. Our deepest view into the cosmos comes from studying the cosmic microwave background radiation, the CMB. This faint glow fills all of space and represents our baby picture of the universe, showing how it appeared when it was only 380,000 years old and first became transparent to light. In this ancient radiation, we see tiny temperature variations, fluctuations of just a few millionths of a degree. These seemingly insignificant ripples were the seeds from which all cosmic structure would eventually grow. Every galaxy cluster, every superstructure, every cosmic filament we've explored began as one of these minute temperature differences in the primordial universe. But how did these structures grow so large? The answer lies in a period called cosmic inflation, which occurred in the first fraction of a second after the Big Bang. During the first 10 to 32 seconds, a time interval so brief it makes a nanosecond seem like an eternity, the universe expanded faster than light, increasing its size by at least 10.26 times. This inflationary expansion helps solve one of cosmology's greatest puzzles. When we observe the cosmic microwave background in opposite directions in the sky, we're looking at regions that are now separated by nearly the entire observable universe. According to our understanding of physics, these regions could never have communicated with each other during the universe's history. Light hasn't had enough time to travel between them. Yet these disconnected regions have almost identical temperatures. How did they become so perfectly synchronized if they were never in contact? Cosmic inflation provides an answer. Before inflation, these regions were close together and had time to reach thermal equilibrium. Then inflation stretched space so rapidly that these once connected regions were flung to opposite sides of our observable universe. If cosmic inflation is correct, then our observable universe represents just a tiny fraction of a much larger reality. The entire cosmos could be infinitely larger than what we can see, containing structures that dwarf even our observable universe. Our 93 billion light-year sphere of observation might be like a grain of sand compared to the infinite beach of total reality. Some cosmologists propose that inflation never completely stopped, but continues in other regions beyond our cosmic horizon, constantly creating new bubble universes like ours. In this multiverse scenario, each bubble universe could have different physical constants, different laws of physics, and therefore entirely different types of cosmic structures. As we approach these extreme scales, our understanding of fundamental physics begins to break down. Near the edge of the observable universe, our knowledge of gravity, space-time, and causality reaches its theoretical limits. The very concepts we use to define structure and object may become meaningless. 73% of our universe consists of dark energy, a mysterious force that's causing cosmic expansion to accelerate. This dark energy is literally pulling the universe apart, and its effects become more pronounced over time. Eventually, it will separate the great superstructures we've explored, isolating each galaxy cluster in an island of space. The acceleration of cosmic expansion means that in the far future, the cosmic voids will expand until they occupy virtually all of space. The magnificent filaments and superstructures we've explored will be torn apart, leaving behind isolated islands of matter, floating in an ocean of ever-expanding emptiness. Even now, we can detect the influence of these massive superstructures through something called the Sunyaev-Zeldovich effect. Hot plasma within galaxy clusters leaves subtle shadows in the cosmic microwave background radiation, allowing us to map massive structures even when they're too distant to see directly. Computer simulations using our best understanding of physics can successfully recreate the formation of cosmic structures we observe, but they begin to fail when modeling scales approaching the observable universe's size. At these extreme scales, the assumptions underlying our physical theories may no longer apply. Perhaps the structures we observe exist at precisely the scale they do because they're necessary for the formation of galaxies, stars, planets, and ultimately life itself. This is known as the anthropic principle, the idea that we observe the universe we do because it's the only type of universe capable of producing observers like us. Think about what we've discovered on this journey. We began with human-scale objects and progressed through increasingly vast structures, solar systems, stellar neighborhoods, galaxies, galaxy clusters, superclusters, cosmic filaments, and finally, superstructures spanning billions of light years. Each step revealed that what seemed enormous at the previous scale was actually tiny compared to what came next. But now we've reached a different kind of boundary. It's not just that we lack the technology to see farther or measure larger structures. We've encountered the fundamental limits of what can exist as a coherent structure in our universe. Beyond the observable universe lies what we literally cannot know, because no information from beyond that boundary can ever reach us. The largest structures we can confirm scientifically are the superstructures we've explored. Cosmic formations, billions of light years across, containing hundreds of quadrillions of solar masses, representing significant fractions of all the matter in the observable universe. These may indeed be the largest objects that can exist in any meaningful sense. We've arrived at the very limits of confirmed science, standing at the edge of the knowable universe and peering into regions that may forever remain beyond our reach. Standing at the frontier of observable cosmic structure, we face a revolutionary possibility that challenges our very conception of what constitutes an object in the universe. What if the cosmic web itself, every filament, every superstructure, every void we've explored, should be understood not as separate components, but as a single integrated entity spanning the entire observable cosmos? This paradigm shift requires us to abandon our human-scale intuitions about objects and boundaries. Instead of viewing the cosmic web as a collection of separate structures, we must consider it as one vast organism, a unified system where every galaxy, every cluster, every void plays a role in maintaining the architecture of the whole. Picture the most complex structure you know intimately, your own brain, with its billions of neurons connected by trillions of synapses. Your brain forms an intricate network where individual cells communicate across the entire organ through electrochemical signals. The cosmic web bears a striking resemblance to this neural architecture, with galaxy clusters acting as nodes connected by filaments that stretch across 93 billion light-years of space. Each galaxy cluster in this cosmic brain contains hundreds or thousands of galaxies, making them far more complex than any individual neuron. Yet just as neurons work together to create consciousness and thought, these galactic nodes work together to create the large-scale structure that defines our universe. The comparison becomes even more compelling when we realize that both systems show similar statistical properties in their connectivity patterns. At every scale we've examined, from individual galaxy clusters to massive superstructures to the largest filaments, we observe similar patterns repeating endlessly. This fractal nature suggests that the cosmic web might function as a coherent whole, with structure emerging at multiple levels simultaneously, like the branches of a tree that divide and subdivide, creating complexity through repetition of simple patterns. The self-similarity extends across scales that span dozens of orders of magnitude. Galaxy clusters group into superclusters, which group into larger structures. which connect through filaments in patterns that mirror the way smaller structures organize themselves. This hierarchical organization suggests an underlying unity that transcends any individual component. The average density of our universe is remarkably sparse, just 5 protons per cubic meter of space, far emptier than the best vacuum chambers we can create on Earth. Yet the cosmic web concentrates this diffuse matter into structures that are 100 times denser than the cosmic average, while leaving vast voids that contain almost nothing at all. This extreme organization suggests a level of coordination that extends across the entire observable universe. The cosmic web doesn't just collect matter randomly, it sorts, organizes, and distributes it according to patterns that emerge from the interplay of gravity, dark matter, and the expanding fabric of space-time itself. Computer simulations reveal something extraordinary about the invisible scaffolding of dark matter that underlies all visible structure. Dark matter flows along cosmic highways, billions of light-years long, carrying ordinary matter with it like debris caught in invisible rivers. These streams of dark matter connect our local cosmic neighborhood to structures 10 billion light-years away, creating an unbroken network of gravitational influence. The dark matter filaments act like the circulatory system of the cosmic web, transporting not just matter, but gravitational information across vast distances. Changes in density at one location propagate through these channels, influencing the growth and evolution of structures separated by distances that light takes billions of years to cross. What's perhaps most remarkable is that galaxies on opposite sides of the observable universe move in coordinated patterns, as if responding to the same vast gravitational symphony. Entire regions of space flow in concert toward massive attractors, creating coherent bulk motions that span significant fractions of the observable universe. This coordination suggests that the entire cosmic web functions as an integrated system, a single entity with emergent properties that arise from the interactions of its countless components. Like a flock of birds or a school of fish, the cosmic web exhibits collective behavior that transcends the actions of any individual galaxy or cluster. Think of the cosmic web as the universe's internet. Just as the global internet connects computers worldwide through cables and wireless signals, the cosmic web connects every galaxy through invisible conduits of dark matter and energy. Information travels through this network not as digital signals, but as gravitational influences that propagate at the speed of light through the fabric of space-time itself. The analogy extends further when we consider that just as the internet enables emergent phenomena like global communication and collective intelligence, the cosmic web might enable cosmic-scale phenomena that we're only beginning to understand. The coordination of structure formation across billions of light years suggests information processing capabilities that dwarf any earthly computer. If we consider the cosmic web as a single entity, its total mass equals approximately 10 to the 53 kilograms. That's the number 1, followed by 53 zeros. To put this in perspective, if every atom in your body was scaled up to the size of a galaxy, you would still possess only a tiny fraction of the structural complexity contained within the complete cosmic web. This mass isn't distributed uniformly, but organized in patterns of incredible sophistication. The cosmic web processes matter and energy on scales and timescales that challenge our understanding of what it means for something to be a single, coherent system. Over the past 13 billion years, this vast network has evolved like a single organism, with each region influencing the growth and development of every other region. Galaxy formation in one area affects star formation rates across vast distances. The birth and death of massive stars sends shockwaves through space that can trigger or suppress galaxy formation millions of light years away. The evolutionary history of the cosmic web shows remarkable coordination across time as well as space. Periods of intense star formation occur simultaneously in widely separated regions. Galaxy mergers happen in synchronized waves. Even the formation of supermassive black holes appears to follow coordinated patterns across cosmic distances. Although limited by the speed of light, gravitational influences do propagate through space-time as ripples in the cosmic fabric itself. These gravitational waves allow distant parts of the cosmic web to communicate with each other, coordinating the flow of matter and energy across impossible distances. Recent discoveries of gravitational waves have revealed that space-time itself carries information about cosmic events. The cosmic web might use these gravitational signals as a form of long-distance communication, with massive structures sending and receiving signals that coordinate their evolution over cosmic time. Certain regions of the cosmic web function like cosmic hearts, pumping matter through the filamentary network. The Great Attractor, which we encountered earlier, serves as one of these gravitational engines, drawing matter from across hundreds of millions of light years and redistributing it through connected filaments. These gravitational engines work in concert, creating a circulation system that moves matter and energy through the cosmic web's vast structure. Like the cardiovascular system in a living organism, this circulation maintains the health and continued evolution of the entire system. The cosmic web resembles a vast three-dimensional sponge where the solid framework, the filaments containing galaxies, occupies only about 5% of the total volume. The remaining 95% consists of cosmic voids, yet this seemingly empty space plays a crucial role in determining the web's overall architecture. The voids aren't simply empty space, but active components of the cosmic web structure. They expand under the influence of dark energy, pushing against the filaments and helping to maintain the web's overall geometry. Without these voids, the cosmic web would collapse under its own gravity. Across this vast network, cosmic phenomena occur in synchronized patterns that suggest coordination on unimaginable scales. Star formation rates, galaxy mergers, and even the birth and death of massive stars happen in coordinated waves that sweep across the cosmic web over billions of years. These synchronizations cannot be explained by simple gravitational attraction alone. They suggest that the cosmic web operates as an integrated system with feedback mechanisms that coordinate activity across its entire structure. At these maximum cosmic scales, our familiar concepts of individual objects begin to lose meaning. Everything is gravitationally connected to everything else through the web's intricate architecture. The boundaries between separate structures dissolve when viewed from this perspective, revealing a single, unified system that encompasses everything we can observe. The cosmic web exhibits something analogous to the butterfly effect on scales that dwarf our imagination. A collision between galaxy clusters in one region can send gravitational ripples through the web's structure, influencing the flow of dark matter and ultimately affecting galaxy formation in regions billions of light years away. These cascade effects demonstrate that the cosmic web possesses a form of memory, where events in its distant past continue to influence its current evolution. Like a vast neural network, the cosmic web integrates information across space and time, creating patterns of extraordinary complexity. This vast network appears to have its own form of metabolism. It processes dark energy and dark matter, converting them into the visible structures we observe, stars, planets, and ultimately the complex chemistry that makes life possible. The cosmic web feeds on the fundamental forces and particles of nature, transforming them into the magnificent architecture of galaxies and clusters. The metabolic processes of the cosmic web operate on timescales of billions of years. Yet they show remarkable efficiency in converting the universe's fundamental ingredients into increasingly complex structures. This cosmic metabolism has ultimately produced the conditions necessary for life itself. Some scientists speculate whether a structure this complex and interconnected could develop emergent properties that transcend the behavior of its individual components. Could the cosmic web, over billions of years of evolution and increasing complexity, develop something analogous to awareness? While this remains pure speculation, it highlights how our journey toward the largest possible objects leads us to questions that transcend physics and venture into philosophy. The cosmic web's ability to process information, coordinate activity across vast distances, and evolve toward greater complexity suggests capabilities that challenge our understanding of what constitutes consciousness. We have reached the point where the very notion of searching for the largest object in the universe becomes inadequate to describe what we've discovered. The cosmic web represents something that transcends our normal categories of thought. Not merely large, but encompassing, not simply massive, but architecturally fundamental to the nature of reality itself. Now we must confront the deepest question our journey has revealed. Why does the human mind struggle so profoundly to truly comprehend these cosmic scales? And what does our inability to fully grasp such vastness tell us about the relationship between consciousness and the universe it seeks to understand? As we stand at the threshold of ultimate cosmic comprehension, we must confront the most profound question our journey has raised. What constitutes the absolute largest possible object in existence? The answer forces us to grapple with the very boundaries of reality itself. The ultimate cosmic horizon is the observable universe, a perfect sphere 93 billion light-years in diameter, containing everything we can possibly detect or that can physically affect us. This represents the absolute limit of what we might consider a single, coherent entity. Beyond this boundary lies not just the unknown, but the unknowable. To help you visualize this ultimate scale, imagine that every galaxy we've discovered, all 2 trillion of them, were individual houses scattered across a vast metropolitan area. The observable universe would be a city so enormous that even traveling at the speed of light, you could never hope to visit all its neighborhoods. Light itself, the fastest thing in existence, would need 93 billion years to cross from one edge of this cosmic city to the other. Here we encounter a fundamental limit imposed by the nature of causality itself. Nothing can be larger than the observable universe in any meaningful sense, because regions separated by more than 93 billion light-years have never had the opportunity to communicate or influence each other. They exist in complete isolation, unable to coordinate or interact in any way. This raises a profound philosophical question that strikes at the heart of what we mean by object. When something becomes so vast that it encompasses everything we can know, everything we can measure, everything that can possibly affect us, does it still make sense to call it an object? Or has it transcended the category of thing and become synonymous with reality itself? Consider the information content of this cosmic totality. The observable universe contains approximately 10^120 bits of information. This number is so staggeringly large that if every atom on Earth were converted into the most advanced computer possible, Working for billions of years, they could not process even a tiny fraction of this cosmic information. Think of it as the ultimate library. If each bit of information were represented by a single letter, the observable universe would contain more books than there are atoms on Earth. And each book would have more pages than there are stars visible to the naked eye. This cosmic library contains the complete history of every star, every planet, every possible arrangement of matter and energy across 13 billion years of cosmic evolution. At these extreme scales, even the geometry of space itself becomes mysterious. Near the cosmic horizon, space-time may be curved in dimensions our three-dimensional intuition cannot visualize. The familiar concepts of distance and direction that guide our daily lives may break down entirely when applied to the universe as a whole. We face an unprecedented measurement problem. How do you measure something that contains all possible measuring devices? The observable universe is the ultimate standard of size precisely because there is nothing outside it to provide comparison. It defines the very concept of large rather than being an example of something large. To escape from the observable universe, an object would need to travel faster than light for longer than the universe has existed, a physical impossibility that violates the fundamental laws of nature. We are trapped within this cosmic sphere not by physical barriers, but by the constraints of space-time itself. Picture ourselves as explorers on a vast island surrounded by an infinite ocean. Our island, the observable universe, represents everything we can ever hope to know directly. The ocean beyond our shores may contain other islands, other worlds, but they might as well be imaginary for all the difference they make to our existence. The boundaries of our cosmic island are not fixed, but constantly expanding. Every second, the observable universe grows by approximately 300,000 kilometers in all directions, as light from previously unreachable regions finally arrives at our telescopes. We are constantly discovering new territory that was always there but remained invisible until now. Yet even as our observable universe expands, we encounter hints of even more fundamental limits. At the smallest scale, the Planck length of 10^35 meters, the very concept of distance begins to break down. Space-time itself becomes grainy and uncertain, suggesting that there may be ultimate limits to how large structures can become, just as there are limits to how small things can be. Despite its immensity, the observable universe contains a finite amount of energy, approximately 10^69 joules. This is equivalent to about 10^52 hydrogen bombs, an almost incomprehensible amount of energy, yet still finite. This energy budget places fundamental constraints on what kinds of structures can exist and how large they can grow. Our discoveries have revealed a troubling paradox. According to our best theories, the universe should appear homogeneous, perfectly smooth and uniform, when viewed on scales larger than 300 million light-years. Yet we've discovered structures billions of light-years across that violate this expectation, suggesting our understanding of cosmic evolution remains incomplete. We've reached the point where our physics begins to fail us. Our mathematical models and physical theories struggle to describe what might exist beyond the observable universe. It's like trying to use mathematics to describe what lies beyond mathematics itself. The tools we use to understand reality become inadequate when applied to reality's ultimate boundaries. We find ourselves in the position of fish trying to comprehend the ocean while confined to a small aquarium. Our perspective is fundamentally limited by our position within the very system we're trying to understand. We can never step outside the observable universe to gain an external view of its true nature. If cosmic inflation continues in regions beyond our observation, It may be constantly creating new bubble universes like ours, each with its own physical laws and structures. In this scenario, our entire observable universe, vast beyond comprehension, becomes infinitesimally small compared to the eternal inflationary cosmos. This reveals the ultimate relativity of cosmic perspective. An observer in a distant galaxy would define their own observable universe, which would partially overlap with ours, but extend into regions we can never see. The concept of largest structure becomes fundamentally dependent on who is doing the observing. As we reach these ultimate scales, the very language we use to describe reality begins to collapse. Words like size, object, and largest lose their precise meanings when applied to structures that encompass everything knowable. We've pushed human language and concepts to their absolute limits. The question, what is the largest object in the universe, may be fundamentally unanswerable, not because we lack the technology to find the answer, but because the question itself becomes meaningless at cosmic scales. We've discovered that reality transcends our ability to categorize and measure it. At the boundary between the known and unknowable, we face a humbling truth. The search for the largest object in the universe has led us not to a definitive answer, but to the limits of what conscious beings can comprehend about the cosmos they inhabit. Standing at this cosmic threshold, we must now turn inward and examine what our journey through these impossible scales reveals about the nature of human consciousness, our place in the vast cosmic web, and the profound mystery of why beings as small as ourselves can contemplate structures so unimaginably vast that they challenge the very foundations of knowledge itself. Our exploration of cosmic scales has led us to a profound paradox that strikes at the heart of human existence. We are infinitesimally small compared to the vast superstructures we've discovered, yet we are simultaneously the only known beings capable of comprehending and mapping these cosmic immensities. This contradiction reveals something extraordinary about the nature of consciousness itself. Imagine an ant standing in the center of a football field, but this ant possesses not only awareness of the field's boundaries, but the ability to map entire continents. Measure the circumference of the Earth and calculate the distance to the Moon. This is precisely our situation in the cosmic hierarchy. Being so small, we're invisible on galactic scales, yet capable of understanding structures billions of times larger than our home galaxy. In all the vastness we've explored, from cosmic filaments to superstructures spanning billions of light years, consciousness may be so extraordinarily rare that a single planet harboring aware beings could be more precious than entire galaxies of lifeless matter. Think about that. All those trillions of stars, all those countless worlds. Yet the emergence of minds capable of contemplating cosmic architecture might be rarer than the rarest cosmic phenomena. The temporal perspective is equally humbling. Your individual existence spans perhaps 8 decades in a universe where the largest structures took 13 billion years to form. If the entire history of cosmic structure formation were compressed into a 24-hour movie, all of human civilization, from the first cities to space exploration, would occur in the final frame of the final second. Yet in that infinitesimal moment of cosmic time, human consciousness has managed to map structures across the entire observable universe. We've traced the cosmic web's architecture, measured the masses of galaxy clusters, and detected structures so large they challenge our fundamental theories about cosmic evolution. Our telescopes function as instruments of transcendence, extending our senses across impossible distances and allowing us to touch objects billions of light years away. When the Hubble Space Telescope captures light from a distant galaxy, That light has traveled for billions of years to reach us. In a very real sense, we're making contact with ancient cosmic structures, reaching across space and time to gather information about the universe's deepest mysteries. The mapping of cosmic superstructures represents one of humanity's greatest collaborative achievements. Thousands of scientists across decades have worked together, sharing data, refining techniques, and building upon each other's discoveries to create our current understanding of large-scale cosmic architecture. This collective intelligence transcends what any individual mind could accomplish, demonstrating that consciousness becomes even more powerful when it works in concert. Perhaps most remarkably, this cosmic knowledge has been democratized in ways previous generations could never have imagined. Anyone with internet access can explore high-resolution images from the Hubble and James Webb telescopes, examine three-dimensional maps of cosmic structure, and participate in citizen science projects that contribute to our understanding of the universe. Each person becomes a potential cosmic explorer, capable of contemplating structures that dwarf their wildest imagination. This accessibility reveals a profound truth about human significance. Our apparent cosmic insignificance is precisely what makes our capacity for understanding so extraordinary. We are points of conscious light in vast oceans of darkness, tiny flames of awareness capable of illuminating and comprehending structures immeasurably larger than ourselves. Think of yourself as a single candle flame in an enormous cathedral. Individually, you seem insignificant compared to the vast architecture surrounding you. Yet that small flame can illuminate the entire space, revealing details and patterns that would otherwise remain hidden in darkness. Your consciousness, however small in cosmic terms, has the power to illuminate and understand structures spanning the entire observable universe. The connection between human consciousness and cosmic structure runs deeper than metaphor. The atoms that compose your body were forged in the nuclear furnaces of ancient stars that died billions of years before our solar system formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar cores and distributed through space by supernovae, becoming part of the cosmic web's material flow. You are literally made of star stuff that has traveled through the cosmic web for billions of years before becoming organized into the complex patterns we call life and consciousness. In a very real sense, you are the universe becoming aware of itself, cosmic material organized in such a way that it can contemplate its own vast architecture. Understanding cosmic scales can fundamentally transform how we view human problems and concerns. When you grasp that our entire civilization exists on a tiny world, orbiting an ordinary star in one galaxy among trillions, surrounded by structures billions of light years across, it puts daily worries into profound perspective. Not to diminish human experience, but to place it within the vast context of cosmic time and space. If we are indeed the only conscious observers in our region of the cosmic web, this places upon us a unique responsibility. We become the universe's only witnesses to its own magnificent architecture. The preservation and expansion of knowledge about cosmic structure becomes not just a scientific endeavor, but a cosmic duty, ensuring that the universe's grandest constructions are observed and understood and remembered. Every photon we capture from distant cosmic structures is like an archaeological artifact from the deep past. Light from the most distant galaxies began its journey when the universe was young, carrying information about conditions and processes that existed billions of years ago. We are cosmic archaeologists, piecing together the history of structure formation from these ancient messengers. Although our individual lives are brief, the discoveries we make about cosmic architecture will remain valid for as long as the universe exists. In this sense, understanding the cosmic web grants us a form of intellectual immortality. The knowledge we gain about billion light-year structures will outlast our solar system, our galaxy's current form, and perhaps even the stars themselves. This raises a profound question about cosmic loneliness. If other civilizations exist somewhere in the vastness of the cosmic web, are they also standing on tiny worlds, using their own instruments to map the same cosmic structures, feeling the same mixture of insignificance and wonder that we experience? Are there other conscious beings contemplating the same cosmic web from different vantage points, each seeing a slightly different piece of the vast puzzle? The pace of our cosmic discoveries is breathtaking. In just 1 century, we've progressed from believing our galaxy was the entire universe to mapping superstructures billions of times larger than the Milky Way. If our rate of discovery continues to accelerate, what revelations await us in the next 100 years? What cosmic structures might we discover that dwarf even the superstructures we've explored? We live during a unique epoch in cosmic history. The cosmic structures we observe today are visible because the universe has expanded just enough to separate them clearly, but not so much that they've been scattered beyond detection. In the far future, accelerating cosmic expansion will carry these structures beyond the reach of any possible observation. Future civilizations will inherit a much emptier, lonelier universe. This temporal privilege makes our current era special in cosmic history. We are among the first generations of conscious beings to map the cosmic web's full architecture, and we may be among the last to see it clearly. Our observations are capturing the universe during its most structurally rich and observable phase. Perhaps the search for the largest object in the universe has revealed something even more remarkable than any physical structure. The emergence of consciousness capable of comprehending cosmic vastness might be the universe's greatest achievement. Maybe the true largest object isn't a superstructure of matter and energy, but the collective human consciousness that can map, measure, and find meaning in cosmic immensity. Our journey through cosmic scales reveals that size is always relative, but our capacity for understanding appears to be absolute in its reach. A consciousness that evolved on a tiny world can somehow grasp structures that span the observable universe. This suggests that awareness possesses a kind of cosmic citizenship that transcends physical scale. Standing at the culmination of our cosmic journey, we discover that seeking the largest structures in the universe has led us back to ourselves, not because we are large, but because we are extraordinarily capable of comprehending largeness. Now we must synthesize these discoveries and explore what our cosmic journey reveals about the relationship between consciousness and the vast cosmos it seeks to understand. Our cosmic odyssey has fundamentally transformed what we mean when we ask about the largest object in the universe. We began seeking a single, definable entity, perhaps a massive galaxy or cosmic structure, but discovered that at extreme scales, the very concept of individual object dissolves into something far more profound, interconnected systems that defy our everyday categories of thought. Think of a symphony orchestra performing a magnificent piece of music. You wouldn't point to the loudest note and call it the music. The symphony exists in the relationships between notes, the harmonies that emerge from their interaction, the complex patterns that unfold across time. Similarly, the largest structures in the universe aren't simply big objects, but cosmic symphonies, intricate harmonies of matter, energy, space, and time that create something greater than the sum of their parts. Our journey revealed a cosmic hierarchy that stretches across unimaginable scales. Particles organize into atoms, atoms into molecules, molecules into planets. Planets orbit stars, stars cluster into galaxies, galaxies gather into clusters, clusters connect through filaments, filaments weave the cosmic web. Each level emerges from the complexity of the level below. Yet where does this hierarchy end? Does it continue beyond our ability to observe or even conceive? We've discovered a fundamental paradox in our quest for cosmic understanding. The largest structure we can definitively measure is limited by our position within the very cosmos we're trying to comprehend. We are simultaneously observers and participants, measuring instruments and part of what we're measuring. This isn't just a practical limitation, it reveals something deep about the relationship between consciousness and reality. Every cosmic structure we've explored, from our solar system to the vast cosmic web, demonstrates that absolute separation is an illusion. Everything is gravitationally connected to everything else. The cosmic web reveals this interconnectedness at its grandest scale, a universe where isolation is impossible and every component influences every other component across space and time. Consider your family tree. You know your parents, perhaps your grandparents, maybe a few generations back, but your ancestry extends infinitely into the past, connecting you to countless individuals you'll never know. Our cosmic family tree works the same way. We can trace our connections from Earth to the solar system, to the galaxy, to the cosmic web. But these connections extend far beyond what we can directly observe. The transformation of human perspective over the past 5 centuries is breathtaking. 500 years ago, we believed Earth was the center of all existence. Today, we understand ourselves as inhabitants of a tiny world orbiting an ordinary star in one galaxy among trillions, embedded within cosmic structures of unimaginable vastness. This shift in perspective represents one of consciousness's greatest achievements. What makes this cosmic awakening even more remarkable is its accessibility. Today, anyone with internet access can explore detailed images of distant galaxies, examine 3-dimensional maps of cosmic structure, and participate in the same sense of cosmic wonder that drives professional astronomers. The universe's grandest architecture has been democratized, making every person a potential cosmic explorer. This raises a profound question about the relativity of significance. If we are infinitesimally small compared to cosmic superstructures, then our human creations, our art, music, literature, acts of love and kindness, are infinitesimally small squared. Yet does this mathematical insignificance diminish their value? Perhaps significance operates by different rules than physical scale. We exist like conscious water droplets, aware of our individuality while simultaneously understanding that we're part of a vast ocean. Each droplet is unique, with its own temporary form and trajectory, yet made of the same substance and subject to the same forces as the infinite ocean surrounding it. This dual nature, individual yet universal, may be the key to understanding consciousness's place in the cosmos. The temporal dimension adds another layer to our cosmic perspective. The largest structures we've discovered will persist for trillions of years, long after our sun burns out and our galaxy merges with Andromeda. Yet these eternal structures possess no consciousness to appreciate their own magnificence. Our brief existence, fleeting as it is, might be more cosmically significant than their vast durability. This suggests an intriguing possibility about cosmic purpose. Perhaps the universe didn't create these immense structures to be inhabited, but to be comprehended. Maybe consciousness itself is the universe's way of understanding its own architecture. In this view, every human mind that grasps cosmic scale becomes an instrument through which the universe observes itself. If we are indeed the only known beings capable of mapping cosmic architecture on these scales, we bear a unique responsibility. We become the custodians of cosmic knowledge, tasked with preserving and transmitting our understanding of universal structure. This knowledge becomes a sacred trust, not just for humanity, but for the cosmos itself. Each cosmic discovery becomes like finding a new volume in an infinite library. We can read only a tiny fraction of the books during our brief visit, but each one we understand adds to consciousness's cosmic comprehension. Our task isn't to read everything, an impossible goal, but to read as deeply as possible while we're here. We face a profound communication challenge. How do we convey the reality of billion light-year structures to minds that evolved to understand walking distances and human lifespans? Language itself becomes inadequate when describing realities that transcend all earthly experience. Yet somehow, consciousness finds ways to stretch beyond its evolutionary boundaries and touch the infinite. Our concepts of size, distance, and age have undergone revolutionary expansion. Words that once described earthly experiences now encompass cosmic realities that dwarf our home planet. This conceptual evolution demonstrates consciousness's remarkable ability to adapt its categories to accommodate ever larger realities. Throughout our cosmic journey, we've observed remarkable unity underlying cosmic diversity. The same physical laws that govern falling apples also orchestrate the dance of galaxies. Gravity, electromagnetism, and nuclear forces operate consistently from the smallest particles to the largest superstructures, creating unity within unimaginable diversity. Standing at the limits of observable cosmic structure, we must ask whether our science has reached its ultimate boundaries. If something exists beyond the observable universe, our current methods cannot detect it. We may have arrived at the edge of possible knowledge, where further exploration requires not just better instruments, but entirely new ways of thinking about reality. Perhaps we are like seeds of understanding planted in a cosmic garden of unimaginable scope. Our role might be to grow in comprehension until we can eventually understand the entire system that gave us birth. Each generation of cosmic discovery represents growth toward this ultimate understanding. Our search for the largest object in the universe has revealed something unexpected. The quest itself has led us to fundamental questions about consciousness, meaning, and our place in the cosmic order. We sought to measure the universe and discovered instead that the universe might have created us to measure itself. After traveling mentally across billions of light years and contemplating structures that dwarf our wildest imagination, we now return to human scale with our perspective forever transformed. Like mountaineers who have climbed to an impossible peak, we haven't grown larger. But our view of the valley below, our everyday existence, has changed in ways that can never be undone. The paradox we've uncovered is profound. In searching for the largest object in the universe, we discovered that the question itself reveals more about human nature than about cosmic architecture. Our quest illuminated not just the vastness of space, but the remarkable capacity of consciousness to transcend the physical limitations of the bodies that house it. If consciousness truly is rare in the cosmic web, and evidence suggests it might be extraordinarily scarce, then every moment of human understanding about superstructures and cosmic filaments represents an exceptional event in the history of the universe. Each time a human mind grasps the scale of billion light-year structures, the cosmos achieves something it has rarely, if ever, accomplished before. The giant structures we've studied function as cosmic mirrors, reflecting back to us our own extraordinary ability to transcend physical limitations through pure thought. A being weighing perhaps 70 kilograms, standing on a world that's invisible from the nearest star, can somehow comprehend and map structures containing the mass of hundreds of quadrillions of suns. When we observe distant cosmic structures, we're looking into the past, seeing these formations as they existed billions of years ago. But when we understand what we're seeing, we create knowledge that will persist into the future, connecting different epochs of cosmic history through the bridge of consciousness. We become temporal connectors, linking the ancient cosmos to its distant future. The democratization of cosmic wonder is one of our era's most remarkable achievements. Today, a curious child with access to a small telescope can observe galaxies within distant superclusters, participating in the same cosmic exploration that has engaged humanity's greatest minds throughout history. The universe's most magnificent architecture has become accessible to anyone with the curiosity to look up. This accessibility represents a revolutionary moment in human history. For thousands of generations, humans lived and died without ever knowing that galaxies existed beyond our own. The cosmic web, superstructures spanning billions of light years, the vast filamentary architecture of reality, all of this remained completely hidden from human awareness until just the last few decades. Now, any person with internet access can explore these cosmic wonders in detail. The atoms that comprise your body tell a story of cosmic inheritance that spans billions of years. The carbon in your cells, the calcium in your bones, the iron in your blood were all forged in the nuclear furnaces of massive stars that died before our sun was born. You are made of stellar remnants that have traveled through the cosmic web for eons, finally organizing themselves into the complex pattern we call a human being. This makes you a direct heir to the largest structures in the cosmos. The superstructures we've explored aren't just distant objects to admire, they're part of your family tree. The cosmic ancestry that made your existence possible. Every breath you take contains atoms that once resided in the hearts of dying stars, dispersed through cosmic filaments, and eventually found their way to Earth. The heavy elements in your body, everything except hydrogen and helium, were created during the violent deaths of massive stars scattered throughout the cosmic web. These stellar explosions dispersed their nuclear products across vast distances, where they became incorporated into new generations of stars, planets, and eventually living beings. You are literally made of ancient starlight, stellar ashes organized into consciousness. Our knowledge of cosmic structure represents a precious inheritance that we must preserve and transmit to future generations. Understanding of the cosmic web, superstructures, and the largest formations in the universe constitutes a unique form of human heritage. Cosmic knowledge that has taken centuries to accumulate and that future explorers will build upon. This responsibility weighs heavily when we consider that we might be the only conscious beings in our region of the cosmic web. If other intelligent civilizations exist, they may be separated from us by distances so vast that we'll never know of each other's existence. This potential cosmic loneliness makes the preservation of knowledge even more critical. Think of consciousness as a small candle flame in a vast cathedral. Individually, that flame seems insignificant compared to the immense architecture surrounding it, yet that tiny light is capable of illuminating the entire space, revealing details and patterns that would otherwise remain hidden in darkness. Human consciousness, however small in cosmic terms, possesses this same illuminating power. The analogy becomes even more powerful when we consider that without the candle flame, the cathedral remains dark and unknowable. Similarly, without consciousness, the cosmic web's magnificent architecture exists but goes unappreciated, unmeasured, ununderstood. Consciousness serves as the universe's method of self-illumination. The human capacity for cosmic wonder may be one of the most extraordinary characteristics to emerge in the universe's entire history. This ability to feel awe in the face of structures billions of times larger than ourselves might be rarer and more precious than the structures themselves. After all, what value does magnificence have without consciousness to appreciate it? Wonder appears to be a uniquely conscious phenomenon. The cosmic web doesn't appreciate its own beauty. Superstructures spanning billions of light years exist without any awareness of their own grandeur. Only consciousness can transform raw cosmic architecture into something meaningful, beautiful, worthy of contemplation. If other civilizations exist within the vastness of cosmic superstructures, do they experience similar wonder when contemplating the same cosmic web that surrounds us? Have they developed their own understanding of billion light-year filaments? Do they feel the same mixture of insignificance and awe when mapping cosmic architecture? This possibility suggests a cosmic fraternity of contemplation, minds scattered across the universe but united in their capacity to appreciate cosmic grandeur. Perhaps across the cosmic web, other conscious beings are conducting their own surveys of large-scale structure, making their own discoveries about cosmic filaments, feeling their own version of the wonder that drives human cosmic exploration. Understanding cosmic scales has the power to transform human perspective in profound ways. When you truly grasp that our entire civilization exists on a tiny world within one ordinary galaxy, among trillions, embedded in structures that span billions of light years, it becomes difficult to view human conflicts with the same intensity. This cosmic perspective doesn't diminish human concerns, but places them in context. Personal struggles remain real and important, but they occur against a backdrop of unimaginable vastness. Political boundaries seem arbitrary when viewed against cosmic structure. National differences fade when we recognize our shared cosmic citizenship. We reveal ourselves as fellow explorers of a shared cosmic home. Every human being, regardless of nationality, culture, or background, shares the same cosmic address, residents of Earth, third planet from the Sun, located in the Orion arm of the Milky Way galaxy, member of the local group, part of the Virgo supercluster, embedded within the Laniakea supercluster, connected to the vast cosmic web. In the deepest sense, we are all cosmic relatives. Every human being is made of elements forged in the same stellar furnaces, shaped by the same cosmic forces, contemplating the same magnificent structures that define our universal neighborhood. The cosmic web that connects distant galaxies also connects each of us to every other conscious being. This cosmic kinship extends beyond humanity to all life on Earth. Every living thing shares the same stellar ancestry, the same cosmic elemental heritage. The carbon-based chemistry of life links all terrestrial organisms to the nuclear processes that occurred in ancient stars distributed throughout cosmic superstructures. We live during a uniquely privileged epoch in cosmic history. For the first time since the universe began, technology allows us to map structures that remained invisible throughout all previous human history. We are the first generations to see the cosmic web clearly, to understand our place within superstructures, to grasp the true architecture of reality. This privilege comes with temporal limitations. In the far future, accelerating cosmic expansion will carry distant structures beyond the reach of observation. Future civilizations will inherit a much emptier, lonelier universe, where the cosmic web's magnificent architecture has been scattered beyond detection. We live during the universe's most observable epoch. The discoveries we make about cosmic structure will remain valid for billions of years, long after our individual lives have ended, long after our civilization has become memory. In this sense, understanding the largest structures in the universe grants us a form of immortality. The cosmic knowledge we create becomes part of the universe's permanent record. Every measurement of cosmic distance, every map of large-scale structure, every discovery about superstructure masses and extents adds to an eternal library of cosmic knowledge. This information will remain accurate as long as the universe exists, making our brief lives participants in something truly permanent. In a cosmos where structures persist for billions of years, while human lives span mere decades, each moment of cosmic understanding becomes infinitely precious. The briefness of our existence doesn't diminish its significance, it amplifies it. Every instant of cosmic comprehension represents an extraordinary achievement against overwhelming temporal odds. Consider that the cosmic web took 13 billion years to evolve its current architecture, while human civilization has existed for only a few thousand years, and scientific astronomy for merely a few centuries. In this impossibly brief cosmic instant, we've managed to map the universe's largest structures. Science serves as our vehicle for transcending physical and temporal limitations. Through telescopes and mathematical models, we become contemporaries of events that occurred billions of years before we were born. We touch the ancient universe, measure its properties, and understand its evolution as if we had witnessed it directly. When we observe the cosmic microwave background radiation, we're seeing the universe as it existed when it was only 380,000 years old. When we study distant superstructures, we're witnessing cosmic architecture as it existed billions of years in the past. Science makes us time travelers, observers of epochs we could never directly experience. In the end, we are points of conscious light scattered through a vast cosmic darkness, tiny yet capable of illuminating and comprehending structures infinitely larger than ourselves. Our small size doesn't diminish our significance. It makes our achievements more remarkable. We are the universe's way of coming to understand itself. Perhaps the greatest object in the universe isn't a physical structure at all, but consciousness itself, the phenomenon that allows matter organized in a particular way to contemplate the cosmic web, measure superstructures, and find meaning in vastness. If this is true, then every human mind capable of cosmic wonder becomes part of the universe's greatest creation. The emergence of consciousness from cosmic evolution represents an extraordinary phase transition in the universe's development. For billions of years, matter organized itself into increasingly complex structures, stars, galaxies, cosmic filaments, but remained unconscious of its own magnificence. Only with consciousness did the universe develop the capacity for self-reflection. Our journey through cosmic scales reveals that while the largest object in the universe may remain impossible to fully imagine, Our capacity to attempt that imagination, to reach beyond our evolutionary boundaries and touch the infinite through thought, might be the most extraordinary phenomenon in all of cosmic history. We began seeking the largest object in the universe and discovered instead that we ourselves represent something far more remarkable than any structure we could measure. We are conscious matter capable of understanding its own cosmic context. Tiny beings with infinite reach, brief flames of awareness capable of illuminating the eternal architecture of reality itself. The search for cosmic vastness led us home to the recognition that consciousness, however small and brief, possesses a significance that transcends all physical scale. Every moment of cosmic understanding represents a triumph of mind over matter, awareness over indifference, meaning over meaninglessness. In contemplating the largest structures in the universe, we've discovered that the most extraordinary thing isn't their size, but our ability to comprehend that size. The cosmic web may span billions of light years, but consciousness spans the gap between the infinitely small and the infinitely large, making every human mind a bridge between the microscopic and the cosmic, the temporal and the eternal. If you're still awake, it's because the content was really good. So, take a moment, leave a like and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.